I think you are muting.
Amri, your mic is muted.
Yeah, so we go on to the second lecture of this conference. This is also the first of a series of lectures by Professor Tomoyuki Arakawa of RIMS Kyoto University. His lectures are going to be on vertex algebras and representation theory. Professor Arakawa, please.
Thank you very much for the invitation. So I'd like to talk about, I'd like to give introduction to vertex algebras. So my plan is the following. So today I give a quick introduction to vertex algebras. And then tomorrow I talk about some construction of vertex algebra called BRST reduction, and explain W algebras, which are one of the most important and interesting examples of vertex algebras. And then I talk about the representation theory of W algebras. And so there are very exciting new developments around vertex algebras. And if time permits, I'm going to explain some of them. Okay, so let's start. So everything will be over a complex number unless otherwise stated. Also, vertex algebra makes sense for any characteristic. And V is going to be a vector space over C, usually infinite dimensional. And I talk about formal series which values in operator varied formal series, and I expand this formal series in this way always. So An is the coefficient of G2 minus n minus 1. So this notation means coefficient of G in this. And
Arakawa, your audio is not very clear. Maybe if you can move closer to your microphone, or maybe.
Okay, so maybe it's closer to my laptop. Can you hear me now?
Not sure, but yeah, maybe it'll be better. Let's see.
Okay, maybe I try to increase the. So okay, so there we are. So this formal series called a quantum field. So it's a field if applied to any vector of V, you get only finite many negative power of Z. So which is the same that if I use this notation, n applied to V is 0 for sufficiently large n. And I denote the span of fields on V as field of V. So this is a subspace. And I should note the, so if you have two fields, multiplication is not very defined. Not very defined in general. So this is just a subspace. Can you hear me now? Can you hear me?
Yes, it's better now.
Okay, so so now I can define vertex algebras. A vertex algebra is a vector space V equipped with this this data. So we have a special vector V in V, which is called a vacuum vector, and a linear map T, which is called the translation operator, and a linear map from V to the space of fields of V, which sometimes I denote by YAG or AG, and satisfying these actions. There are three actions. So one is for the vacuum vector. So the image of a vacuum vector by this map must be identity operator on V, and if you apply any YAG to this vacuum vector, we get this. This belongs to this affine space. So this means that if you put G equals to 0, we recover this vector A. And a translation operator behaves like a differential. And the most important property is this locality condition, which is this condition. So I said that multiplication of AG and BG doesn't make sense, but because I changed the variable here by W, so this bracket makes sense as element of this. And if you apply enough power of G minus W, this must be 0 in this vector space. So this is the end of the definition. I'm going to spend some time to explain what this locality means. But first, let me explain the most simplest case that is when vertex algebra is commutative. And vertex algebra is called commutative if this is already 0 without multiplying any power of G minus W. So this is the condition. So in terms of Fourier modes, this means that the bracket of any AM and BN, which is, so this is, I forgot to say, this is operator on V. So this operator always commute. So I think this makes sense to call it a commutative. And there's a theorem by Borchers, who introduced the vertex algebra, that the commutative vertex algebras are the same as a differential algebras. And by differential algebra, I mean a unital. This is a unital, a commutative shear algebra with a derivation. So it's a commutative algebra with a derivation. So the commutative algebra for associate with the vertex algebra is vertex algebra itself. The multiplication is defined by this -1 product. So the statement is that if vertex algebra is commutative, this defines multiplication which is associative and commutative, and also the unit is the vacuum vector, and T is the corresponding derivation. So this gives a structure of differential algebra. And conversely, if you have a differential algebra, which is a commutative algebra with a derivation, you can give R commutative structure of commutative vertex algebra by setting the vacuum vector to be just 1, and translation operator to be this differential. And this operator corresponding A is given by this formula, which is the same, which is defined by sum of n factorial t to n a. So this is some form of series. So this means if you apply v, you get some element of v r in this way, and you can check that this gives you a commutative vertex algebra structure. So the commutative vertex algebra is something very easy. It's just a commutative algebra with additional structure, which is a differential. So T behaves like T is a differential. Now, now I want to explain what happens when vertex algebra is not commutative. So I want to explain what this locality condition means. And there are some equivalent conditions for this locality condition. So the first statement is that so AG and BW are local if and only if this bracket can be expanded in this way. So Cj are some fields on V. So this is some formal series, and this is some formal series defined in this way, and this is called a formal delta function. So AG and BW are local to each other if and only this bracket is expanded in this way. And it can be also phrased as follows. So now there are two conditions. So if you apply, if you consider AG and BW, this can be expanded in a similar way. So here, tau GW is an expansion of this function in the region when G is bigger than W. And this is is a formal series defined. This is called a normal ordered product. And so if you apply BW, if you consider BWAG, you get the expansion of the same function, which is expanded in the opposite reason when W is bigger than G. So this is the statement. And so following physicists, we write this or equivalent to this as this in this way and call it operator product expansion of AG and BW. So when I write this means that the AG and BW are local and so expanded in this way. And so let me explain a part of proof to give you some feeling if you haven't seen this. So the proof of this direction is very easy. You just have to notice this formal series. So this is just a sum over all n. This is a difference of the expansion of the same function 1 over G minus W expanded in the different region. So this is expanded when G is bigger than W, so it's expanded in this way. And here it's expanded where W is bigger than G, so expanded in this way. And if you sum up, you get this formal series. So if you differentiate j times, you just get this difference. So if you substitute this from this, you just get this expression for the commutator. So this is very easy. And the direction from second statement and the first statement is very easy also. So you just have to notice that this expansion defines embedding of rings. So this defines embedding of this into this fields. So this is not a ring, but this is a subspace which forms a field. And so this defines embedding in this field. So if you apply g minus n to this differential of this delta function, you can put this inside, and you get this expression. And if n is greater than k, this is just a polynomial, so you don't have to expand. So you get the same element here. So this difference is 0. So if bracket is expanded in terms of this derivative delta function, if you apply enough power of g minus w, you get 0. And so the state equivalence of this and this state, that the element which are killed by some power of g minus n has to be a sum of derivative delta function, which is not difficult to see. Okay, so I tried. So this OPE, or equivalently the locality, is the most important property or notion in vertex algebra. So I'd like to make some more words. And so we have this identity in the formal series. So this means if AG and BW and has this OPE, and this CJW can be uniquely determined by AG and BW by this formula. And now this statement is also very easy to see. So let me explain why. So we want to look at the coefficient of G inverse in this formal series. So this is by definition difference of expansion of the same function in a different region. So you can think this as a residue in the complex analysis, but if of this function g minus w to n minus j minus 1, but this is expanded where g is greater than w. So when you take a contour, you have to take this kind of a contour so that the g is bigger than w, and you have to take contour when w is smaller than w is bigger than g. So the difference is just a contour around w. So you get the delta n minus j. So we can. So in the computational vertex algebra, we use this kind of trick frequently. And so similar residue calculation, using similar residue calculation, you find that the following statement equivalent. So as OP OPE, so AG and BW are local, and OP has of this form, and if and only if the commutation relation satisfy commutation relation of AM and BM is given by this form. So in other words, OPE is equivalent to the commutation relation of operators. So OPE gives some compact form of commutation relation of this infinite many operators. Now, so as I said, a product of two elements doesn't make sense, but you can somehow make sense of some operation which might you might view as product of fields. So I define nth product of two fields as this. So you look at the coefficient of this little bit complicated formal series of G inverse. But this already appeared when n is non-negative, because so when n is non-negative, you don't have to expand. So this is just the formula that appeared here. So this means so when AG and BW are local, this is 0 for sufficiently large n by definition. So this is 0 for sufficiently large n. And OPE is written in terms of this nth product. And if you compute a -1 product, you get the normal ordered product I defined earlier. And if you compute a -n product to the identity operator, you get some derivative of the original field. And if you have three mutually local operators, then nth product and CG are mutually local. So nth product is closed under mutually local fields. So now I can explain Boucher's identity of vertex algebra. And the statement is that for vertex algebra, so if you have this operators associated with an, and an is operator. So this is element of V. So you can think the corresponding field, and this is simply the nth product of the product field for A and B. So this is what Boucher's identity says. And if you recall this relation, this means that the operator product expansion of YAG and YBG is expanded, is expressed in this way. So in terms of Fourier modes, this relation is equivalent to this relation, which already appeared earlier. Here, this is a finite sum because AJB is 0 for sufficiently large J. But and this relation can be written as this one. And this one has infinitely many terms. However, this makes sense. So this is an element of operator on V. And this makes sense as operator on V because this is both of this is 0 for sufficiently large J. So this identity makes sense as an operator on V. And these two relations are called Boucher's identities. So any questions so far? So now I want, sorry. So now, so this is Vertex. So now I want to explain how we can construct such a Vertex algebra. So there's a natural way to construct a Vertex algebra. If you have a set of mutually local fields on a vector space N. So you can start, for example, from one field, which is local to itself. So mutually means it has to be local to itself also. And you consider the subspace of the fields generated by element of this an identity operator and the successive operation of nth product. So this is a smallest subspace which contains these fields and identity operator, which is invariant under the nth product operation for any n. And the statement is this big space has a structure of a vertex algebra with a vacuum vector is identity operator and the translation operator is a differential. So this space is closed and differential because of this property of nth product. And yeah, so the corresponding field corresponding AG is given by this one. So AGN. So this is considered to be an operator which sends BG to AG and BG. So anytime if you have such a field, you can construct a vertex algebra. And in general, if you have a vertex algebra, you can consider a vertex algebra generated by this field. And the statement is that this one is isomorphic to V. And the inverse map is given by this correspondence. Here, so I didn't explain what is a homomorphism of vertex algebra, but I think it's clear. For two, if you have two vertex algebras, a linear map is called homomorphism of vertex algebra if it's compatible with a vertex algebra structure, which means a vacuum vector has to go to vacuum vector, and the translation operator has to go to translation operator, and it's compatible with nth product. And because of this proposition, we often identify the state, which is V, and the space of fields on V. And let me explain an example. Let G be simply algebra, and we take a normalized invariant inner product, which is Killing form divided by 2 times a check, where a check is a dual constant number, and you have the corresponding affine Katsumori algebra, which is defined by this computational relation. And so we can talk about the representation of G hat, and representation of G hat is called smooth if this one is a field on V, which means that each element is killed by xtn for sufficiently large n. So in particular, highest weight representation is a smooth representation. And for any smooth representation, so because OPE is equivalent to the commutation relation, and this commutation relation shows that these are mutually local, and we have this operator product expansion. So if you have a smooth jihad module of level K means K acts as a constant multiplication by this number K, then you have a vertex algebra generated by this field X0. So this is a vertex algebra. And the corresponding field satisfies this condition, which means that this space is a jihad module because OP is equivalent to the commutation relation of jihad. So this means that this space is this is type. This is a jihad module of level K on which xtn acts as this n squared. And it's easy to check that the xgn kills identity operator for if n is non-negative. So we have a jihad module homomorphism from this induced module. Here, gt acts as 0, and the k acts as multiplication by k. So we have this kind of jihad module homomorphism. And the statement is that this map of the algebra homomorphism is always surjection for any smooth jihad module M. And there's a unique vertex algebra structure on this induced representation, which makes this as a homomorphism of the vertex operator for any smooth jihad module M of level K. And so this vertex algebra with this vertex algebra structure is called universal affine vertex algebra associated with G at level K. And this vertex algebra structure is uniquely determined by the property that the vacuum vector is 1 sine n. So this is the highest weight vector of this induced module. And so I can identify G with this induced module by this correspondence. Then the field corresponding to element of G is just X. Okay, so now.
So maybe this is a good time to see if there are any questions. We can take a few questions. If there are any questions, please just unmute your microphone and ask. Okay, looks like no questions at this stage. Maybe we'll just proceed and yeah, let's go on.
Okay, so now what is module of a vertex algebra? So we call a vector space a module of a vertex algebra if there is a vertex algebra homomorphism from void to this space or some set of mutually local mutually, no, it's not commuting, it's mutually local. So this is a big mistake. Mutually local fields on M. And can show that about a module of so this happens if and only if you have such a map satisfying this Boucher's identity. So you can Boucher's identity is you can regard as this Boucher's identity as a fundamental relation of the vertex algebra. So now, example. So any smooth G-hat module of level K is a G-hat is a module of this universal affine vertex algebra, because we have this surjective map of a vertex algebra. And conversely, any VKG module is a smooth G-hat module of level K, on which this one acts as this nth product. And by this correspondence, you can identify the category of VKG module with a smooth G-hat. We don't need this cup. Smooth G-hat module of level K. So this is the equivalence of categories. So you may think this universal affine vertex algebra as a enveloping algebra of affine algebra, in the sense that the representation of theory is the same. But you might say that this is not so interesting because you don't really have to define vertex algebra to study representation of affine algebra. But you can take a quotient of this the universal affine vertex algebra. As you already seen that for any, so this one is in general a quotient of this universal affine vertex algebra. And in fact, any quotient as a structure of vertex algebra because of this property called a skew symmetry property. So this is the same as this one. So this means left module is also a right module. So left module is automatically ideal. So if you have a vertex algebra, and if in V submodule, which is invariant under the action of translation operator, then quotient is automatically structure has a structure of vertex algebra. So in particular, we can talk about we can take the unique simple quotient, unique simple graded quotient of this universal affine vertex algebra, which is a quotient of VKG by some maximal graded G submodule. Because it's graded, it's invariant under the action of T. And so this has a structure of the vertex algebra, and it's simple as a module by itself. And the category of module over this simple affine vertex algebra is a full subcategory of category of VKG module, which is the same as category of smooth G-hat module of level K, consisting of objects such that the field corresponding to this vector submodule N is identical with 0. And for some value of K, this category becomes very interesting. And that's one of the subject of the study of the vertex algebra. And there's another important example, which is Virasoro vertex algebra. So this is a Virasoro algebra with this commutation relation. And we define the field corresponding to LZ as this one. So for some reason we shift n. So we have use -2 instead of -1. And for any smooth L module of central charge C, the central charge C means that this big C central element acts as identity as C. The commutation relation means that this LZ is local to itself and has this OPE. So you can consider vertex algebra generated by this LZ. And this has a special property that the translation operator is the same as multiplication by L-1. Sorry, this is wrong. Sorry. This is LG 0. So translation operator is inner for this Virasoro vertex algebra. And this is a module. So the story is the same as the case of the affine vertex algebra. So this space, this vertex algebra becomes a module of a Virasoro algebra on which Ln acts as this. So if you consider this kind of induced module, here Ln acts as 0 for and C acts as C. Then we have a surjective map of a module of a Virasoro algebra. And there is a unique vertex algebra structure in this induced module, which makes this map a homomorphism of a vertex algebra. So this vertex algebra structure is uniquely determined by Y of. So first for the vacuum vector is of course 1 tensor 1, and the Y of L-2 0. G is LG. And it has a special property that the translation operator is -1. And this one is called the universal Virasoro vertex algebra with central charge C. And so exactly in the same way as the case of the affine vertex algebra, so module of Virasoro algebra is the same as a smooth L module of central charge C. So this is the kind of, again, enveloping algebra of Virasoro algebra. And this L0 defines a grading of this vertex algebra. So this is eigenvector of L0 with eigenvector delta. So there's a unique simple graded quotient, a simple quotient of the Virasoro algebra, which I did not view C. And vertex algebra is called conformal if there exists a vertex algebra homomorphism from some universal Virasoro vertex algebra to V, such that the image of L-1 coincides with the translation operator and L0 acts semi-simply on V. And the image of this L minus 2, which generates this field, is called a conformal vector or stress tensor in physics. And this number is called central charge of V, which is an important invariant of vertex algebra. And the L0 eigenvalue is called conformal weight of V. So because by definition, L0 acts semi-simply, so V is graded by this conformal weight. So you can talk about the formal character, which is defined by a trace of this operator. This is just a normalization of term. And when this each homogeneous subspace is finite dimension. This is often called normalized character. So, for example, so Virasoro vertex algebra is by definition conformal. The character is written in terms of this eta function. And for simply algebra, this universal affine vertex algebra is conformal with some central charge, provided this denominator is non-zero. And the conformal vector is given by this formula. So this is essentially the same. So this is correspond to a second Casimir element. So second Casimir element gives the conformal vector of the universal affine vertex. And so the definition of vertex algebra naturally extends to the vertex superalgebra. So we are not going to talk much about it, but the more important example is this one. So you consider a Clifford algebra with odd generators, Cauchy n and Cauchy star n, which satisfy this condition. So because it's odd, this bracket means anti-commutator. And then you consider this kind of module of this Clifford algebra. So this is generated by a vector. Generated by a vector 0 satisfy this condition. And so as a vector space, this is isomorphic to a tensor product of this Grassmann algebra of infinite variables. And this is the structure of a vertex superalgebra such that the field corresponding to this one is this and this, and OPE satisfied is given by these formulas. I think I'm doing too quickly. Any question?
Okay, can I ask, so if I have a lowest weight module, say a lowest weight Verma module, that's not smooth.
That's not smooth.
Right?
No, yeah, no. Yeah.
So the lowest weight representation is not captured by the vertex algebra.
It's not captured.
Is that,
you can replace Borel for finite algebra, but not for the whole.
Okay, great, thank you.
But you can, there are a non-highest weight representation. You cannot capture a lowest weight module, but there are a non-highest weight modules which are very interesting. especially in connection with 42D duality, but then not to talk about it. So maybe so if you don't have any more question, I proceed to the next section. So far I only explained the example of a vertex coming from the algebras.
I'm sorry, may I ask one question?
Yeah.
So the question about the super algebras. So when you define normal ordering for the super algebras, is the definition the same as for the usual vertex algebras, or some modifications needed?
Some sign modifications needed, I think. So
I see.
So this was something like AG plus BW plus BW AG minus, but if you need some sign here, because you something like -1 to BA.
Okay, thank you.
So so far I already explained the example which are coming from the algebra. So you might think it's not so interesting, but there are examples, many interesting examples which are not coming from the algebras. And so I'd like to talk about them. So especially double algebras. So there's a way to several ways to construct new vertex algebra from non-vertex algebras. So one of it is just a tensor product. So this is very elementary construction. If you have two vertex algebra, tensor product is a vertex algebra. So the field corresponding A tensor B is just the product of YAG and YBG. And there's a little bit more non-trivial construction, which is called BRST construction. So if you remember Boucher's identity, the computational relation for this zero mode becomes very simple. So a commutation relation between A0 and Bn is just this. And A0 kills this, and T commute is in general, we have translation operator has this property. So especially if n equals to 0, you get this formula. So if you have some operator and consider the kernel of this zero mode, this is naturally a vertex subalgebra of B, because you have so if you have two elements are killed by this one, so this is something like n q0 b, and this is 0, and this is q0 a n, so this is 0 also. So the subspace is closed under this nth product. So this becomes a subalgebra. And if further a square of this element with 0, you can consider corresponding cohomology, which is defined by a kernel by image. And this has a structure of a vertex algebra. So let me explain example. So consider the simplest real algebra SL2, which is spanned by E and H and F. And I consider this two tensor product of vertex algebra. So this is a vertex algebra associated with SL2. And this is vertex algebra associated with super algebra explain, which we usually call it fermions. And I define Q, which is odd element, by this by this. And by state field correspondence, this defines element Q. And you find that the operator product expansion is just 0. So this means a square of Q0 is 0 because Q is odd. So you can take corresponding cohomology. And cohomological degree is taken so I consider this Psi has -1 degree, and this one has 1 degree, and the other element has degree 0. So this is a G-graded space. And this is the structure of the vertex superalgebra. And so this doesn't give you, for SL2, this doesn't give you anything new, but it's interesting because we have a cohomology vanishing, and we recover the Virasoro algebra in this way, where K central charge of the Virasoro and a level of SL2 is related by this relation. So in this way, so maybe I will not talk about much later. I mean, much more. So what is nice about this construction is that this construction is functorial. So if you have any smooth G-hat module of level K, you can consider this tensor product. And this becomes a module of this vertex algebra, which is CKSL2 I just defined. And Q0 has to act as square of this operator is 0. So we have the corresponding cohomology. So we get the functor from, so maybe I go here, smooth SL2 hat module of level K to the category of module over this H0, which is nothing but the smooth Virasoro module of a central charge CK, which sends M to H0 of this cohomology. And the theorem by Feigen-Frenkel myself is the so using this functor, we get the character of all irreducible highest weight representation of a Virasoro algebra. So representation theory of Virasoro algebra is very difficult, although it looks simple, because it doesn't have a while group. So you cannot apply a standard technique of semi-simple real algebra to study a representation theory of Virasoro algebra. So it's very difficult. It's done by Victor Katz and Feigen-Fuchs, but it's very difficult. But how, if you use this functor defined by a Biarist construction, you don't really need to study Virasoro algebra to know the character of a simple representation. If you just have to know the character of, you just have to know representation theory of S2 hat, and then you apply this functor and get the representation theory for free. So this kind of construction gives a very nice way to study vertex algebra. And so from tomorrow, I'm going to talk about such a construction in details for more general situation. So maybe I stop here for today.
Thank you, Professor Arakawa. Let's thank him. Are there any questions? Please just feel free to unmute and ask.
Can you just go back and remind what is Q0 in this for this BRST?
So this is a field. So you expand in this way. So it's just a zero mode. So so if you write explicitly, it's a sum of En pushy minus n star. So we don't really need number order here. I forgot to say I was omitting tensor product sign. So EG is EG tensor 1 and pushy G is 1 tensor pushy G. So this is actually tensor product plus zero mode of this is pushy 1. So this is a very simple operator.
And for general G, what is this Q0?
So this is kind of yeah. So it's a differential for Chevrolet complex for Lie algebra. So QG in general is something like X alpha G C alpha star G, where alpha is moves over a positive root, and there's some cross term. In general, as we have for the Chevrolet complex for the Lie algebra cohomology, and this is correspond to this part, and plus sum of Cauchy alpha ig, where I is correspond to simple root.
Very good. Thank you. Thank you.
Are there examples of this Q0, Q0 sort of construction in the other cases, such as the affine vertex algebras? I mean, it seems like or is it a special sort of construction? Do you need to go to the super algebra situation to construct examples of such Q0, or are there other simpler examples in just the vertex algebra cases?
So you are looking for non-Lie algebra case. For the algebra case, if you have for the algebra case, it's really the algebra cohomology operator. So for this case, it's just so if you forget G, this is really differential for Lie algebra cohomology. So you can, if you put G, you get the differential for the affine. But for the non-Lie algebra case, I don't know whether there's a natural construction of operator. I'm not sure whether I get your question correctly.
No, I was just asking. I mean, your construction of this. So you said if you have a vertex algebra and you have any q with the
Right,
property that q0 square is 0, then
Right,
that gives rise to a vertex algebra. So
right.
I'm just. So my question is, are there such examples? For example, if you had the universal affine vertex algebra, are there examples of such Qs there, or in other such examples?
So for any element satisfying this OPE, for any operator which satisfies this OPE Q odd, then this condition is satisfied.
When you say Q odd, what do you mean?
Odd means it's a super vertex algebra.
Ah, okay.
Yeah.
Okay. So in the just the plain vertex algebra cases, you wouldn't be able to construct such examples.
If it's not super, it's not this construction is not really so it's really this construction is not common for non-super case. This construction is very common. Just consider kernel of some operator or intersection of some kernel of operator. So this is a standard construction of vertex algebra.
Okay. Thanks.
Sure. Any other questions? Well, so if there are no more questions, let's thank Professor Arakawa for the talk. So we'll meet again at 12 o'clock for Professor Dipendra Prasad's talk. Take a short break until then. Of course, the discussion can go on the Zoom.